Hello, my name's Julian Edgar and I'm the author of this book, Car Suspension, Over 120 Years of Ride and Handling. What I want to do in today's video is take a look at a car that's featured in the book. Its innovation in suspension design like basically nothing seen on modern cars. It's the Citroen 2CV suspension. Let's take a look. So the car dates back to 1948. It was in production for many decades and it was developed by Citroen because they wanted a very cheap car that could be used by farmers and others taking their goods primarily to market. And it had a number of criteria that it had to address. It had to be very fuel efficient, very light, use a small engine. But one of the criteria was it had to be able to cross a ploughed field without breaking any eggs that were being carried. And Citroen engineers really took that on board. It wasn't a throwaway line for them. And they developed an absolutely stunning suspension system, stunning in terms of its technology and its innovation. Let's take a look. So here's a diagrammatic view of the suspension. And if we look, here's the front of the car up this end. We can see there are leading arms, directly leading forward, not semi-trailing or semi-leading, but directly forward. And at the rear, there are trailing arms, again, directly rearwards. Now, there's these cross tubes here and here. Those tubes don't turn. The arms are actually pivoted on bearings at each end of those cross tubes. All right, but where are the springs? Well, have a look here. You can see there's a pull rod there and a pull rod there, and the springs are compression springs within these canisters. Now that means that the springs for both the front and the rear suspension are very close to each other inside these canisters on either side of the car. And in fact, these canisters can actually move back and forward a little bit. Not only there's springs inside, see these volute springs at each end of the canister. So the canister can move back and forth, limited by those springs and by these protruding frame parts. Now that means the front and the rear suspension are interconnected. So what? Well, that has some enormous advantages, and advantages that are not used by any current car that I am aware of. So let's look at this in more detail. Now, here's a diagrammatic view of the suspension system. So here we have the front, so here the rear, and here the front arms, and they're arranged like bell cranks. So they can pull on these rods, and there are the compression springs. So the springs are compressed as the suspension arms move upwards. But remember I said that they're contained within this cylinder that's free to move back and forth against extra springs. So how does it all work? Well, if we go over a bump, the rear of the car is lifted and the rear suspension moves upwards. That compresses that spring there. That's the resisting force for the suspension, but the whole canister gets pulled rearwards, in turn pulling on this rod and causing this to go downwards. So the back of the car is lifted by the bump, but the front suspension pulls downwards, offsetting any pitch that would otherwise occur. Now pitch is the movement like that of the car, and it is pitch which is most disconcerting and most annoying for people actually riding in cars. It's not actually roll accelerations or bump accelerations, it's pitch accelerations, which in fact are cause most unhappiness, your head whipping back and forth, in other words. So what we have here is we have an anti-pitch suspension by connecting the front and rear on an extremely cheap car. Most times when you look at suspension and it's elaborate or sophisticated or technically advanced, it's on expensive cars. But this was on a very, very cheap car. All right, what about damping? Well, damping was similarly innovative. On the arm pivots of the front and rear arms, there were friction dampers. Now, friction dampers were widely used in the 20s, but in the 40s they were completely replaced. You had hydraulic dampers, and yet they chose to retain friction dampers because it was so cheap. But what they found was they had wheel hop problems. In other words, the tyres would be bouncing on the pavement. And so they added tuned mass dampers to the wheel hubs to stop tyre hop. Now, a tuned mass damper, in this case, looked like this. It was a vertical cylinder. It had a weight in here, which I'm showing with the mouse. The weight was suspended on a coil spring, and this cylinder was partly filled with oil. And as this weight slid up and down this shaft, bouncing on the spring, its bounces offset the bounces that were occurring of the tyres. In other words, they had a similar resonant frequency, but they were out of phase, so one cancelled the other. And as this weight moved up and down, the oil got squirted through this orifice and actually lubricated the whole system. So tuned mass dampers to prevent tyre hop and friction dampers to damp body movements. Really stunningly innovative. Now, how does it actually translate? Well, I was lucky enough when I was researching on the book to actually be able to examine a 2CV, a more recent one, and I was able to make some measurements of it. And I measured what are called the natural frequencies. Now, that's the rate at which things like to keep bouncing. And the lower the natural frequency, the softer the suspension. So the front natural frequency was 1.4 hertz, which is fairly soft, but not incredibly so. The rear bounce frequency was 1.6 hertz. You always run a higher rear frequency than front frequency to try and stop pitching even when you don't have interconnected suspension. And also here where most weight would go in the back with loading, you need stiffer springs. The pitch frequency of cars is normally somewhere between the front and rear bounce frequencies, except when you have the suspension interconnected, and then it can be lower, a softer pitch frequency, 1.2 hertz. And in roll, also very soft, 1.2 hertz. Now, how does it actually translate to performance on the road? Well, it's a car with a lot of roll. It has a ground center roll center, a ground level roll center, which is going to create roll, and it doesn't have any anti-roll bars, this car, but it gave staggeringly good ride. Now, I was able to go for a ride in the 2CV. The guy who owned the car lived on a farm with a really muddy, rutted track going to his house, which was just an absolutely perfect test for the car, given the criteria against which it was designed. And we drove up and down this muddy, rutted track. It had depressions and washaways and dips of sharp dips too, of about that much. And the ride was unbelievably good. Just astonishingly good. I could not get my head around how soft the ride was and how these bumps did not intrude. Just once the car hit its bump stop and I could actually feel a slight jerk, but otherwise it just glided over this incredibly bad surface. It was a road that I'd driven up a little earlier in my wife's Mercedes. The Mercedes was just driving and riding absolutely horribly compared with the 2CV. Now, is the 2CV a car for a racetrack? Absolutely not. But by gosh, its suspension is incredibly impressive in terms of its innovation, in terms of its cost, and in terms of its outcome. And dare I say, there are no cars that I am aware of, current cars, that have suspension anywhere near that innovative. It's just recycling the same old, and yet this car was an absolute breakthrough. That's why you look at history, and that's why you make judgments based on what has come before. Otherwise, you can just start assuming everything is as wonderful as it ever has been, and that's simply not the case. The book's called Car Suspension, Over 120 Years of Ride and Handling. I go right back to buggies of the 1890s and then go right forward to cars like current cars like Porsche running air suspension, McLaren F1, a whole range of cars. But it gives it a context and understanding that I don't think many people actually have, and it's so fascinating looking at those suspension systems, what they achieved and how they achieved it. The book's out now. Thank you.